So this is the Water Reservoir Storage Project by Kirsten Grace, Supapan Thamanak, and Leticia Zarata-Lungi. So for our design, we chose to do a classroom demonstration model of a pumped hydro storage system. The way these systems work is that you have an upper reservoir and a lower reservoir of water connected by a piping system outfitted with a turbine and pump. So the water from the upper reservoir will drain through the piping and the water turbine down to the lower reservoir, and this will generate electricity. And then the water from the lower reservoir will be pumped back up to the upper reservoir, and this will use energy. So the general idea is that you can store water in the upper reservoir until electricity is needed and let it flow down through the generator and create the electricity, and then just pump the water back up whenever electricity is abundant or cheap. So for our model, we are aiming for at least 70% efficiency, a controllable flow rate, and transportable in under 50 pounds. Our chosen concept is a dual stream flow system. This just means that there's one pipe for the turbine or the downflow and one pipe for the pump or the upflow. It's similar to existing pumped hydro storage systems, which made it easy to go with. In addition, it's simpler than other designs we had in terms of how it works, how to construct it, and just the fluid mechanics. And more importantly, it does meet our user needs. So for a working prototype, we had a variety of materials. We used food storage containers for our reservoirs, had 0.75-inch diameter PVC piping. For our plumbing and general water movement, we used a turbine generator capable of 10 volts and an aquarium pump capable of 15 volts. The aquarium pump just plugs into a normal wall outlet, which makes it easy to use and operate. We used 3 foam yoga blocks to add additional height for the upper reservoir, creating more head. And in addition, there are 2 basic ball PVC valves that we added after the turbine and after the pump as shutoff valves. This helps control the flow and can easily stop the water if there is a leak or an issue. For our design performance, we met our user need of having the system reset within 5 minutes. Our entire system was fully able to cycle, so completely pump the water both up and down within 4 minutes. Our efficiency was lower than we were hoping for, as shown to the left in the photo. We were able to get 9.42 volts out of the turbine. Our theoretical had us hoping for 13 volts, but at the 9.42, we were able to get a power efficiency of 62%. However, the design is quite portable, and it is great for a classroom, lab, or a table or a cart, and you can easily transport it in a car. It's less than 3 cubic feet and easily able to be carried by one person, maybe 10 pounds max. In addition, we moved about 3.5 liters of water. So the containers are capable of holding 6.5 liters each. We didn't want to completely fill the containers as we didn't want to risk anything overflowing or falling over. And so we added 4 liters of water. And then once the water was drained, just due to where the pump and the turbine were placed, a little bit of water was left over in each container. And so about 3.5 liters were fully transferred. So overall, the project was a success. We hope for future iterations to get the efficiency a little bit higher, but it is a good prototype and does show that pumped hydro storage systems do work.